C'est caché. It's broken, the window. So. There are handouts that I put over there if somebody would like to have those. The handouts of the presentation I put on the table on the top there. Ooh. Shall I start? Uh,
You will defend your PhD, which is about forward-predicting consequences of management strategy of lifetime efficiency of individual results. I will let the different members of the jury to present themselves, and then you will have between 40 and 50 minutes, and then you will suffer from a question of the different members of the jury. Okay? So, so you have roughly 45 minutes.
okay.
You have this point.
So good afternoon, everyone again, and thank you all very much for coming. Today, I'm going to talk to you about the results of my 3 years PhD in France, which is entitled on Toward Predicting Consequence of Management Strategy on Lifetime Efficiency of Individual Dairy Cows. And here's an overview of what I will be presenting to you during the next 45 minutes. Firstly, I will introduce the general background of the thesis, which indicate what was the major focus and why it was interesting to be studied. It's then followed with the general objective and some key research questions that we thought important to be explored for obtaining this thesis objective. I then move to the main part of today's presentation, which include 3 studies that we conducted during this thesis to answer these research questions. However, at the time limitation, I mainly focus on the second and the third study, whereas less attention will be paid for the first study. I finalize my talk with some general conclusion and some points for future research. So my PhD thesis mainly focused on feed efficiency, which is commonly defined as the ratio between energy output in milk over energy intake, which is an increasingly important trait to dairy industry and also other livestock sector to meet the multiple challenges of increasing food demand, of being sustainable and also being profitable. Firstly, according to UNDP, the world population will reach 9 billion in 2050, which means that we need to produce more food to feed this higher number of people. At the same time, more people, this means the length for agricultural activity might be reduced, thus the milk production process needs to be more efficient. Under this context, the dairy industry play an important role compared to other livestock species because of their capability of converting inedible food to edible food for human consumption. Secondly, at the concern of the society for sustainability in agriculture increase, the dairy industry has to find a way to mitigate the nutrient excretion from the milk production process because it has been recognized as one of the significant contributor to the global greenhouse gas emission, which is about 4% of CO2 equivalent, according to the report of Food and Agriculture Organization. And thirdly, because feed costs account for more than 50% of the total variable cost, that means any improvement in the way that animal convert feed to milk output can have a substantial impact on farm profitability. So a general conclusion from this slide is that the improvement of feed efficiency is the key component, is very important for meeting these 3 challenges. As a result, during the last half century, we have observed a massive increase in feed efficiency. However, this is mainly reliant on the increase of milk yield, as resulted from improvement in nutrition, management, and genetics. As you can see here from this plot, in 1940, the milk yield production per cows per year was around 2,000, but nowadays we observe it's about 10,000, which increased more than 4 times. And the main biological basis behind the increase of feed efficiency based on increase of milk yield is normally attributed to the phenomenon called dilution of maintenance, which states that as the cows eat more feed and produce more milk, a smaller proportion of energy intake is used for maintenance, and thus cow more efficient. In this plot, it shows the example that when milk yield increases, the amount of energy required for maintenance is assumed to remain the same. However, as the energy required for milk production increase, this amount of energy for maintenance becomes smaller and smaller in proportion, and cows are thus more efficient. However, the increase of feed efficiency based on increased milk yield is not straightforward, as we have been increasingly and commonly observing the losses in both fertility and health at the same time when milk yield increase. This plot shows that when milk yield increase at the blue line here, we also observe increase in number of cervix per successful conception, which means that there's reduction in conception rates. And it's also very common in literature to find the report on the increase of incidence of metabolic disorder in the high-yielding cows. In this context, of course, besides the fact that we have to buy more money for the cost of treatment, the cost of insemination, there's a more important thing. There's a reduction of productive longevity as resulted from the increase of involuntary culling rates because of the problem of fertility and health. And the consequence of these things is that it might result in impaired benefits of improved feed efficiency, especially when we look at in the long term. And this situation seems to be even worse when animals move to the environment which is different from where they were selected. Here I took an example from Coatley and co-workers in 2011, where they studied on 2 breeds, Holstein and Normandy cows, on high versus low feeding system. As you can see here from this plot, that's when animals move from high to low feeding, from the solid symbol to white symbol over here, there's a reduction in milk yield, and also the same for body condition score. Also, this also results in the reduction of conception rate at first and second insemination in the 2 breed. However, the more important thing is that the response of the 2 breed for the same chain in the feeding system is different. For example, here we see in the red arrows that the Holstein Friesian seem to be more sensible to the chain and feeding system compared to the Normandy in the blue arrows. And it's the same for fertility. And this is normally termed genotype by environment interaction in literature. And this indicates it's important for the dairy industry case, especially on the grazing system, where their environment is more widely variable compared to other livestock species, especially also in the under context of the climate change in the future, where resource might be limited and different feeding system thus will be applied by the farmer. And this also indicates the need of finding a suitable feeding system for a specific genotypes. In order to do this, we need to be able to predict how animals respond in both productive and reproductive performance terms in different environments, especially when we look at in the long term. And one way of doing this is to build a long-term experiment with a large number of animals and with sufficiently wide range of the environment, and thus allow us to give conclusions. Another way of doing this, which is increasingly used in animal science, is using the simulation study. The general idea of a simulation study is that, firstly, we need to try to describe the genetic potential of the animal, which is the performance in optimal condition. I'll come back to this point later. And then induce some rules to modify the genetic potential where if we have the variation in the environment. And this allows to further indicate, to determine which kind of animal will be more suitable, will be more efficient in a certain environment. This was actually the main working activity of my 3 years PhD. Another aspect I think is important, especially under the situation of my PhD, is that because feed efficiency is commonly evaluated in terms of energy, which is called energy efficiency, which nitrogen efficiency also taken into account in terms of energy mass. However, as the attention for nitrogen excretion increase, the nitrogen efficiency is becoming more and more important. In this context, we think that nitrogen efficiency needs to be considered separately from energy terms. And because we initially proposed to build an energy-based model for my thesis, in this context, we were wondering if it's possible to extend the conclusion from the work of my PhD thesis or the model that I have been working on to the nitrogen efficiency model. We think this would only be possible if they are correlated and they are affected by the same factors. So exploring this kind of relationship was also the part of my PhD thesis, and more importantly, this kind of study also at the beginning of the PhD also provide me an opportunity to get involved in the literature about feed efficiency. So eventually, the general objective of my PhD was to develop a model for predicting the consequence of different management strategy on lifetime efficiency of individual dairy cows. And we identified 3 key research questions that we believe that by exploring these questions, it could lead us to obtaining these thesis objectives. The first question is, how does an improvement in energy efficiency relate to the nitrogen efficiency? That's how to represent variability in genetic potential of different individual dairy cows. And then the last question is how to represent the effect of performance and nutritional environment on reproduction and productive lifespans. In the next part of my presentation, I will present 3 studies that we conducted to answer this research question. And I believe that I hope that after this, you will understand more clearly about these research questions. Now I move to study 1. The main objective of study 1 was to study the relationship between energy and nitrogen efficiency, also to study animal and feeding factors that affect energy and nitrogen efficiency and their relationship. It turned out later when we built the database that we did not have sufficient data to focus on animal factors. So in this study, we mainly focused on the effect of feeding factors. In order to do this, we perform a meta-analysis by initially building a database through conducting a literature search using some online searching engine like Web of Science, SandiRed, or Google Scholar. We applied some keywords for searching paper, like you can see over here. And those papers were included in the database need to satisfy some selection criteria that you can find specifically in the thesis. But in general, they need to permit the calculation of energy and nitrogen efficiency. So with this information, with these criteria, I eventually obtained 69 studies, including 306 treatment means. From this data, I calculated energy and nitrogen efficiency, which was simply defined as the ratio between either energy in milk and nitrogen in milk over energy and nitrogen in the diet. During this calculation process, I used some equation from NRC and some feeding value from INRA to support for this process. Another important point I would like to indicate in this slide is that if you look at on these 2 equations, there's appearance of milk yield and dry matter intake, which we thought this might cause an artifact when we studied the correlation between these 2 efficiencies. Because of that, we decided to remove this by taking the ratio between nitrogen efficiency over energy efficiency. And we believe that by analyzing this ratio, the artifact of milk yield and dry matter intake would be removed, and thus the effect of other factors on the correlation might be more clearly examined. In terms of the statistical analysis, the correlation between energy and nitrogen efficiency was studied in 2 ways. Firstly, the inter-study correlation was obtained just simply from the global database, whereas the intra-study correlation was obtained after taking into account the random effect of study. The factors affecting energy and nitrogen efficiency and the ratio were studied using mixed effect model on our software. So in terms of the results, as we expected, partly because of the presence of milky and dry matter intake, we obtain a strongly positive inter-study correlation between energy and nitrogen efficiency, which generally we can say this, an increase in energy efficiency also leads to an increase in nitrogen efficiency. However, when we look at intra-study, this correlation was much less, which partly because of the reduction in the range of the data. For example, here you see about 20, minus 10 to 10. This is about 40. Also, this might indicate that other factors also involved in this explanation for this correlation. For example, I think it's the protein quality or the interaction between energy and protein, which we could not take into account in this study. So thus, I think this kind of conclusion is only valid on what we call it on a general diet. And when we move out of the general diet, the conclusion might not be valid. For example, a common way to improve nitrogen efficiency is to reduce dietary crude protein, but this might negatively affect milk yield, and thus affect energy efficiency, and thus this conclusion is not valid anymore. So what I want to indicate in this conclusion, and especially under the situation of my PhD, is that on the general diet, if we increase energy efficiency by increased milk yield, the dilution of maintenance effect will be placed on both kind of efficiency, energy and nitrogen efficiency. In order to demonstrate for that, from this global database, I took out those experiments that contained the dietary crude protein between 15 and 17, and the proportion of concentrate larger than 40%, which I assume, and which also is commonly recommended in literature, that within this range of the diet, if we change crude protein, there's not much significant effect on milk yield and thus energy efficiency. As I expected, when we increase feed milk yield to increase energy efficiency, we also observe increase in nitrogen efficiency. So here we have, for example, here you see this low yielding cow, this high yielding cow, they are placed on this range of the data. So with this information, I could conclude that we found a strong correlation between energy and nitrogen efficiency. On those, I couldn't show here, but we found the acid detergent fiber, digestible energy, and proportion of concentrate were the general factor affecting energy efficiency, nitrogen efficiency, and the ratio. And thus, we think that it's possible to build one model that can largely account for both predicting energy efficiency and then considering nitrogen efficiency as an add-on. So now I move to study 2, in which we aim to simulate variability in genetic potential for production of different genotype of cows. Firstly, I would like to take a moment just to clarify the term genetic potential because it's normally confusing. In my study and also nutritional model, genetic potential is defined as the maximum performance that animal can express under optimal condition, which is unrestricted high quality feed, water, neutral ambient temperature, or low pathogen load. However, under the situation of my PhD, with the term environment is mainly nutritional environment. So let me get back to the general objective about simulating variability in genetic potential. What kind of general elements we need? In order to do that, we need a lifetime multiple trace model, which is the individual weights version, and needs to be able to work under different nutritional environments. In this context, we have a candidates model, which is named Garant, and was published by Martin and Silva in 2010. We contain all of the elements we need. Especially, this model has shown a very good capability of simulating average pattern of genetic potential of a cows using some data from literature. However, in order to be used under my PhD, where we want to simulate not the average pattern, but different genotype cows, this kind of ability has not been evaluated before for the Garant's model, and that was actually the main working activity for this second study. In the Garant's model, in general, to simulate genetic potential of an animal, the model Garant firstly assumes there is a general trajectory of lifetime priority between life function. The main idea behind this assumption is that the model assumes the shape of the performance traits for all of the cows, all of genotype cows could be share the same shape. An example here, whatever the genotype cows, they could have their lactation curve like this for first, second lactation, and so on. And this also applies for other traits, for example, body weight. After assuming this, in order to simulate the high versus yielding cows, the high versus low body weight cows, the governance model incorporated what so-called genetic scaling parameter, and the responsibility of these parameter is to simply scale this curve up and down, and to assume this is the high yielding cow, this low yielding cow, and this is the high body weight cows in the red curve, and low body weight cow. Especially in the governance model, its trace is regulated by an independent genetic scaling parameter. For example, to simulate, to represent mature size, it's WM parameter, which is the potential for non-labeled body mass at the maturity, or it's the same for other traits in milk and mobilization. After being able to describe genetic potential, the governance model assumes some energy constant to quantify how much energy is needed to meet the genetic potential. In the same way, the governance assumes some predetermined dietary energy density to quantify the dry matter intake needed to have this amounts of energy. So if you look at this approach, the starting point of governance is the genetic potential, which is opposite sign of most of model in literature, where starting point could be dry matter intake. So with this information, what we could ask ourselves is the governance model with this genetic scaling parameter, and by assuming this, is that robust for simulating genetic potential for different genotype of cows. Also, if you want to use governance in the future for simulation study, it is important to obtain the knowledge on the correlation between the genetic scaling parameter and if they are affected by different genotype. In order to test this, we use the model to derive genetic scaling parameter by adjusting the governance model to individual cows observation from an external database, which is completely independent from the database that used for developing governance. And then we use the time trends of the residual from the model adjustment from this step to evaluate the robustness of the model to different breed. So here, actually, what happens? We have governance model with some assumption that I'm not including in this slide, with some genetic scaling parameter. Now, if I have an individual observation on milk yield for one cow into lactation, I could enter this into the governance model and started adjusting these genetic scaling parameter until we observe the best fitted between the model and the observed data on the red curve, mainly based on the root mean square error criterion. And then from this, I computed the residual for studying future, the time trends of the residual, which is simply defined as the difference between fitted and the observed data. I also record the genetic scaling parameter for future analysis of the distribution. All of these fitting processes were performed on the model maker software. In terms of data, we obtained the data from MEMO project, which was a long-term genetic evaluation project, obtained from Aarhus University in Denmark, including 3 dairy breeds, then it's Red and Holstein and Jersey, including 202 cows, 180 lactation. One of the speciality of this experiment was that the cows in this experiment were fed with constant energy density diet throughout lactation cycle, and this amount of energy density were assumed to allow cows to approximately obtain their genetic potential. And that's why it's making this data to be appropriate for testing the governance model. From this data, we had some trace, the record for performance traits and reproductive events. So here is an example how the model fits the data for one cow's individual observation into lactation, here for body weight, for milk yield, milk composition, and dry matter intake. When we look at the distribution of the fitting residual from all individual cows relative to day from calving, what we can see here from day 0 to day 250, we see that all of the residual are distributed around the horizontal line of 0. Moreover, when we compare between breed, we see that we found that no significant difference between breed in the time trend of the distribution of the residual. In this plot, one symbol represents one breed, but I think it's not very important in this case because we plot all of the individual residual in this plot. However, when we look at in the end of the lactation, what we found here is some deviation, especially the underfeeding of milk yolk, which could be explained by the difference in the feeding system that used in the database that we in our study, and also the database that used by developing garants, which is constant feeding in our case and the step-down reduction feeding in the model, in the data for developing garants. In the step-down reduction feeding, the cows in late lactation are normally fed with low energy density diet, which might not satisfy the genetic potential of the cows, and thus the lactation curve of these cows might be reduced more quickly compared to what we obtain from a constant feeding. However, when we look at, even in the case of underfeeding milk yield, this amount of underfeeding milk yield account in general just about 7% of the total milk yield in the same lactation. That means we think it's not a very big problem for a simulation study. Also, because the garants model is supposed in the future to be used for simulating a realistic herd where this kind of feeding is more common, it's really common. So we think that this kind of assumption on the sheep is adequate for the garants model. When we look at the distribution of genetic scaling parameter, what we see firstly, there's no difference between Danish red and Danish Holstein in the mean and the standard deviation of all of these genetic scaling parameter. However, the Jersey cows are separated from the other two breeds. Firstly, especially the body weight, which is representing smaller compared to the other two breeds, and also Jersey had a much higher meal fat composition compared to the other two breeds, represented by the parameter nu-f. When we look at the correlation between genetic scaling parameter, the first, which is obtained from the principal component analysis. Firstly, what we observe is the extent of these correlation were consistent with what reports from literature in the correlation between these traits. Of course, they are really only similar because these genetic scaling parameters are not actually the trait that we observe in the data, but they are just numerically representative of these parameters. Because of this, we think that these correlation between genetic scaling parameters were mainly induced by the biological relationship between the traits and not because of the model architecture. When you look at the right plots on this slide, it's indicate again, it's confirm again the result that we just saw in the last slide, the fact that there's not much difference between Danish red and Danish Holstein in the distribution of genetic scaling parameter. And however, the Jersey are separated from the other two breeds. So with this information, what I could conclude from my second study is that the garant is sufficiently robust to be able to simulate genetic potential for production of a wide range of dairy genotypes. Also, we felt the genetic scaling parameters are largely uncorrelated, which is an important property for future use of garant for simulation study. So with this result, I now move to study 3, where we attempted to use garant, not in the optimal condition, but in the situation where we have the variation in the environment. Before going to study 3, I think it's important to just remind you where we are so far, and I hope this will help you to better follow the rest part of the presentation. So far we have had a garant model with some genetic scaling parameter that allow us to simulate genetic potential. In other words, is the performance in optimal condition. So what happens if now we have the variation in nutritional environment? We need some rules to reflect the response of the animals in this case. Or in other words, the rules to modify these performance. And those rules in my study come from the second study of Martin and Sauvon, published on the same year as a companion paper. And now, so let's go back to the main interest of my PhD thesis, which is on lifetime efficiency. What do we need more in order to calculate lifetime efficiency? So we need Garand to provide information on performance, but not only in 1, 2, or 3 lactation, not in the short term, but Garands need to simulate this over the lifespans of the animals, and thus allow it to determine lifetime efficiency. We know that the lifespan is a variable. There's a variation, which is resulted from either fertility, health, and management factors. At this moment, this information is not existent in the Garand's model, the current version. This was actually the main objective of my first study, was to extend the Garand's model for predicting variation in lifespan, and thus allow studying lifetime efficiency of individual dairy cows under different management strategy. Let me go back to the scheme again. So now we need to build some kind of extension in order to determine their variation in lifespans, which is resulted from fertility, health, and management. So however, under the context of my PhD, for the reason of simplicity, we mainly focus on fertility and management, but not the health aspects. In order to do this, we constructed what we call reproduction submodel, where we take into account these two contributors, the management, and then allow to provide some information on fertility for the Garand's model to simulate performance over the lifespan of the animals. In our study, we assume that the reproduction of the animals is negatively affected by a high milk yield, a low body condition score, and a negative energy balance. And this information that provide for repro is received from the Garand's model. If you look at this circle, what we see is that the Garand simulate performance traits, and these are used as the inputs for a reproduction submodel, and thus the repro use this and provide information on variability in reproductive performance, thus allow Garand to run through lifespans of the animals, and thus allow to determine lifetime efficiency. So in the next slide, I will describe how we constructed reproduction submodel. Firstly, let's go back to the objective. What we are interested in is the variation in the lifespans, which is mainly determined by the fact that either animal is pregnant or not pregnant. So because of that, instead of modeling on an individual step of the reproductive process, we assume a likelihood of conception of a viable calf, which is abbreviated as ALCON, as the final product of the reproductive process, which is the accumulated result from other steps involved toward having a newborn calf. In general, in the reproduction submodel, after parturition, the animal is assumed to have a natural period which follows the normal distribution, has the mean 21.8 and the standard deviation of 3, and after that she's assumed to have a cycle length follow the same distribution. And the insemination occurs after voluntary waiting period of 50 days. During this breeding period, the likelihood of conception is dependent on the level of milk yield, energy balance, and body condition score. And here we also include the number 0.6, which try to reflect the fact that even in the case of absence of these three contributors, we still observe the maximum conception rates about 0.6, which is actually the case of virgin heifer. After this period, if the cow is pregnant, then she's assumed to have a gestation length, follow the normal distribution with a mean 280 and the standard deviation of 5 before she gets calf in here and terminate the lactation cycle. In our study, we assume the effects of milk yield, energy balance, and body condition score to follow a sigma function. As you can see in here, the high milk yield, the low likelihood of conception, the low energy balance, the low body condition score, the low likelihood of conception. Especially, we assume that the body condition score above 3 has no effect on fertility. In terms of the model simulation, the service only starts when we observe the value L count larger than 0.4. The number 0.4 we include in here to try to reflect that there's a proportion of cows that weekly spread estrus, then this proportion of cows might not be detected by the farmer, and of course they are not inseminated. When this condition is satisfied, then insemination are induced by a random draw from a uniform distribution between 0 and 1, and an animal is assumed to be pregnant if this number from the uniform distribution is smaller than Alcon values. We also apply some simple culling policy. If the number of cervix larger than 4 and the milk yield level on that day smaller than 25 kilo, then the cow is culled. If the milk yield is larger than 25 kilo, then the farmer might want to attempt another service. If the animal is not pregnant after 160 days postpartum, then she's culled anyway. All of this reproduction submodel was written on C++ programming language, running on Vocop platform, developed by INRA. Also, in order to evaluate the repeatability of the reproduction submodel, of course in this case, it's not the Garance model, but the reproduction submodel. We ran 20 simulations, and we include 200 animals per simulation. Also, to evaluate the efficiency of the reproduction submodel, we compare our data. We select 2 studies from literature, from Cotillion and co-workers and Price and Coffey and co-worker, where they had 2 different cows herd. In here, from the Cotillion and co-workers, we obtained the cow from a French herd with the name Le Pen, include 2 breeds, Holstein and Normandy, fed high concentrate. And here, this is the Long Hill herd, which is from Scotland, and include 2 selection lines of Holstein cows with fed high versus low feeding concentrate. The procedure to evaluate reproduction submodel is that firstly, we need to adjust the Garance model to have the right performance that we obtain from selected data. For example here, in the individual points or the observation, if I now have the average curve of a Holstein Friesian, what I need to do is that I need to adjust the parameter in the Garance model, which is new y in here, until I observe the best fish, like here, as you can see, which is very similar to what I did in the second study. And then, after doing this, when I obtain the new parameter for new y, I assume this is average representative for this Holstein Friesian herd, because this is the average curve that I obtained from the data. So now, if we want to simulate a population of Holsteins, I apply the information on the distribution of this parameter from the second study to simulate a population of Holsteins. Then we use information on performance that we obtain in here at the inputs for repro model, and just to simulate reproductive performance. And then we use this information to compare back to the selected data. In case of low feeding, it was induced by the energy density parameter. From this information, we also calculated lifetime efficiency, simply the ratio between energy in milk over energy intake over the lifespan of the animals. Under the concepts of my PhD, because of the time limitation, and also because of the availability of data, I assume that all of the cows have the same milk composition, whereas they have a variation in milk yield, represented by the new y, and also they are vary in the body weight and body condition score, without represented by the 3 parameter. In terms of the result, please be noted that this is the new or the updated result compared to the one that I reported in the thesis when I submitted to the jury. So here I show an example how the model simulated the average curve of milk yield and body condition score for a Holstein cows on high feed from Le Pen data. Here's for milk yield and for the body condition score. When we compare reproductive performance, the first thing I would like to indicate in this table is that if you look at these lines, what we see is a very small variation in simulated output between the simulation. That means the model is very repeatable or very consistent. Secondly, the model adequately predicted the first cervix conception rate, 41-38, and also the other interval traits as well. For example, 84, 80, 98, 97. When we compare the reproductive performance of the Normandy cows, what we see is that the model underpredicted reproductive performance of Normandy cows. The same for first cervic conception rate, 48, 58, and also other interval traits. When we compare, I'll go back here. When we compare the lifetime efficiency between the cows, Holstein cows and Normandy cows, what we observe is the model simulated Holstein cows are more efficient compared to Normandy cows, which is even they have lower reproductive performance and also a short-term lifespan compared to Normandy cows. We think this is mainly driven by the level of milk yield. However, in our study, in the current study, we did not take into account the fact that, for example, the longer longevity cows, the longer lifespan of the Normandy can have a more calf during their life, and also the cost of veterinary treatments, the cost of examination that they were not taken into account. When we compare the data for reproductive performance of Langhill data, firstly, the model adequately predicted the first cervic conception of the control and selected cows, 46, 45, 42, and 39. However, when we compare the interval traits, what we observe is the model underpredicted all of these interval traits, which we could be explained by the fact that the voluntary waiting period that we set up in our model is 50 days. But what I obtained from a personal communication from the Langhill data is around 60 days. So we explain by this difference by the difference in voluntary waiting period. But the good news is that the direction of the result were comparable with observed data, which is very important. The selected cows had lower reproductive performance compared to the control cows. And again, high-yielding cows were more efficient, despite they have a lower reproductive performance and shorter lifespan, which is mainly driven by the level of milk yield. So from this information, what I could conclude from my first study on the variation of the lifespan is that the whole Garand repro model consistently simulated productive and reproductive performance of different genotype of cows, and the simulated results were comparable with the selected data. On those, I couldn't show you here, but we found the simulated effect of the feeding level, high versus low concentrate feeding, on the reproductive performance were comparable with the observed data in the case of Langhill herd. And lastly, the model simulated genetic selection for a higher milk yield led to a lower reproductive performance and a shorter lifespan, but did not reduce lifetime efficiency. So with this information, I now move to my last part of presentation, which is a conclusion and some point for future research. So from all of my work during my PhD thesis, what I could conclude is that in general, we have already successfully extended the Garand's model for simulating effect of management strategy on lifetime efficiency of individual dairy cows, in which we already incorporated variability in genetic potential for production to Garand. Also, we provide some initial distribution of genetic scaling parameter for using in the future simulation study. And also, we already include the performance consequence on probability of reproducing, and thus allow to determine the variation in lifespan, and thus go back to allow to determine the lifetime efficiency of different genotype of cows. And lastly, we think that on a general diet, it seems likely that this model can be extended to the lifetime nitrogen efficiency model. Although what we have seen is a very promising results for the Garand's model to be used in the future for a simulation study to simulate lifetime efficiency of different individual dairy cows. But during my discussion, I have also indicated some limitation of my work that lead us to think that there's still a lot of work need to get done in the future if we want to improve the quality of Garand's model. The first thing I think is that to try to incorporate the consequence of performance not only on fertility of the animal, but also on the health and or survivability of the animal, and making this to be one of the determinant of the variation in the lifespan. not only on fertility aspect. Secondly, if you want to evaluate more accurately or more realistically lifetime efficiency, I think it's more important. It's important to not only look at the individual level, where the main focus on milk yield production, but looking at the farm level to take into account for example, the benefits of having a more number of cow produced and also the veterinary treatments and maybe other aspects like environmental aspect, animal welfare aspect could be very important. And finally, we think that it's very important to explore the way how to link the genetic scaling parameter to estimate breeding value for genetic selection of feed efficiency in the future. So these are on the results, all of the information I would like to convey you during this presentation. But before finalizing my talk, I would like to take this opportunity to thank my supervisor, Nicolas Frischkens and Phyllis Smedley, for supervising me during the last 3 years. I thank the thesis committee, including Donna Berry, Yvette Dua, Olivier Martin, and Im Codebo, for their use and advice, and also help me have this thesis when it's on that driveway. Of course, I thank you very much, the thesis jury. They are here for their time to evaluate my thesis and also to be here for evaluating my presentation. Especially, I thank Cloud Evasion for providing me data for the second study. Pierre Blavy, I think he's here, no? For helping me in writing the code for the reproduction submodel. I acknowledge Greenhouse Milk and ReproLab project for co-funding my PhD. Of course, the INRA, one of the team Mozart and Econ Doctoran ABS for hosting me my PhD in France. And lastly, but most importantly, I would like to express my acknowledgement on my family, one of the family members, and also the friends who are here and who cannot be here, unfortunately, for always being with me during my life in Spain, my life in France, especially this person who has been listening to my presentation from the other side of the world, from the small iPad over there. Thank you very much.
We still have 5 seconds.
I was thinking 5 minutes, then I was.
Okay, thank you for this clear presentation. And a very well argumented presentation. So I will ask first questions.
I think to answer this question, it should be starting from the second study and then move to the first study. In the second study, the term that you are just asking, I think the suitable term should be adjustments, because we actually did not simulate or did not try to predict anything in the second study, where we try to derive, or we try to obtain the genetic scaling parameter by adjusting those parameters until the model we obtain the best fitted. So I think the suitable term would be adjustment. And this is also the problem when we try to answer the comments from the viewers for the second study when we submit the paper. So I understand the confusion of that aspect. So I think the main term should be adjustment. That's to be understood. And from the third study, we actually try to simulate the model. I mean, we use the model to simulate the reproductive performance of the animals. So firstly, we adjust the model, adjust the guarantee part to fit the reported data from literature, and then we use this information as an input for the reproduction submodel, and then we start simulating or predicting the reproductive performance, and then we come back to compare.
Okay, but if you adjust the model to observe the actin, next question, the obvious question is then, can you use the model as well to predict if
Well,
they are completely independent?
Yeah, firstly, the data that we use for the second study, what I said is completely independent from the first study, from the data that Olivier Martin used for developing Garen, for calibrating the shape. So what we try in the second study is to try to see if this assumption of the shape, you remember when I presented, that's the Garen's model, assume there's only one general shape, and the question is, if it's possible, only one simple shape can be used for different animals. So if, for example, this shape is not right, is not correct, then when you adjust it, or when you fit it with the observed data, you would expect to obtain a very different between observed and fitted, especially the time trend of the residual. You would see, for example, if the shape is not the same, then the distribution of the residual should have some kind of strength distribution.
You didn't find it.
Yeah, fortunately, we didn't find it. Well, we found a little bit in the end part, the last part of the lactation cycle, but that's what we couldn't be explained by the differences in the constant feeding and the feeding that from the data that the author used for developing caverns. So,
Sorry to interrupt.
Yeah.
I had another question in my mind, actually. What I meant, where I want to go is, could you also use distribution partitioning? You describe, let's say, all the variation between individual animals.
Yeah.
Okay. You adjust the model, you nicely show how much individuals can differ, can vary, in all these different functions. As soon as you fit it, adjust the model for these individuals, can you next test the same model again, the same outcomes for these individuals, to check whether the model actually can predict in future what these individuals are doing?
well, I think to answer your question
Is
is
that
that
possible or not?
I think yes, and also, well, just go back again. The parameter, well, in the governance model, there are two parts. One part to represent the shape, that is called assumption, and there are parameters in that part, but what we call black box. We try to not touch on that part, and then the other part is just genetic scaling parameter, that is just scale up and down. So what we actually did in the second study is to test it, the shape part, the parameter that regulating the shape. And the data that we used were independent from the data that to calibrate the shape. So I think if it's work on the data that we obtained from Aarhus University, then I believe that it's work for, I don't mean all of the cows, but I think, well, at least you see that we have diverse cows. Then it's red and then it's Holstein and Jersey in our case. Low genetic merit cows and high genetic merit cows with 108 cows, 2-3 lactation. So I think it's good, it works.
Yes, I agree. The general patterns and the general patterns and differences between individuals, that matches quite well.
Yeah.
Even though you have data from different birds, independent data, then you
Yeah.
can also describe these patterns. I agree. But I was just wondering, can you actually use it to do predictions from a single individual animal? So you first develop this model, and then you have a description of all this variation between animals. Can
Yeah.
you use it for these individuals?
I think yes.
That's probably not what you did in your studies, but you think you can.
Yeah, I think yes, yeah. Well, we have 108 animals. We have a very diversified, what I show you from the, I think it's the first line. This is okay, this is actually the curve that I draw from the data that I obtained. This one. What's the point? This one. If you see here, we have 3 variables with a very high variability. But the model then finally turned out that we could fit, so the black behind would be have even different. So I believe this work. This is actually the data I obtained from to evaluate the model.
Okay, I'll continue to next issue. Thank you for your answer. In the first study that you published, I think it's chapter 2.
Yeah.
It's about this meta-analysis.
Yep.
You start in your introduction and you mention all kinds of environmental issues, ammonia emissions, things like that. But still, you take digested nitrogen.
Digestible nitrogen, yes.
Yes, but why didn't you use, if you look at dairy farm, I mean, the farmer is really interested in how much of the feed is standing up in the milk. He's not only interested in digested nitrogen, he's also interested in the non-digested parts. Why didn't you do the same study, also including gross nitrogen efficiency? Because that's really important on dairy farm.
So what we think in this case, what was the argument is that if you take into account so in terms of the definition of feed deficiency, this could be, of course, like I agree with you, that can be measured in different level, the gross, digestible, or metabolic, or the net. But to us, in order to evaluate to include that part of digestible, and the argument to take into account the digestible level is that we want to also evaluate the environmental impact. But when you move to the gross efficiency, it's also include the part of feed that is actually not digested by the animals.
Yes.
Yeah. So there is one. If you want to actually evaluate the efficiency, how animal can digest, then because that part is actually indigestible already.
Yes, but you decide to only focus on the metabolic part of the animal.
Yes, that's the main link.
So if we talk about environmental issues, all the feed is not being used by the animal, ends up in the human.
Yeah, but we.
Going into the environment as well.
Yeah, but by doing this, in our study, we also took into account the fact that when you consider at the digestible, you took into account the fermentation process.
Yes.
Yeah, only things that I assume that's different animal, that I assume in our case, that most of animals, the difference in the digestive efficiency could be estimated. But I agree with you that the main part is due to the variation in metabolic and partly the fermentation process.
Okay, so you agree with me that you doing both and show them next to each other, that would be even more interesting.
Yeah.
Then I continue in the same study on page 38. You show, you discuss about high PCO values in diets, and you show the two graphs with ADF content.
Yeah.
ADF less than 21% by
Yeah.
or more. You conclude there's a clear relationship, clearly shows that if PCO is higher, that the animals suffer acidosis and then your efficiency goes down.
Yeah.
That's correct.
Can you repeat your question?
You have figure 3.6 on page 38.
Yeah.
In your discussion, you refer to this figure, and I freely translated, you more or less say that the left graph with the ADF values less than 21% right of the method, that it clearly shows that high PCO values deliver a kind of acidosis in the animals, so that the animals become less energy efficient.
Right.
That's correct.
I think so.
Okay.
Let me show you this as
Yes.
what I try to explain in the idea behind that is that is included in this one.
Yes, these two graphs, correct.
Yeah. Okay. So what we try to argue in that is that in this graph you see that when the IDF is very low, that means we have a high PCO in the diet, and in this part when high IDF, that means low PCO. What we try to argue is that in this part of IDF low, that means we have high PCO in this direction. The main negative effect is caused by the PCO with the acidosis. When we move to the part that have low PCO, normally the increased PCO we have increase in energy efficiency, but because this part we include both PCO and NDF in the model, so the mainly of the effect of PCO in this case, in this situation, is mainly dominated by the effect of low RDF, a high RDF that's mean very high fibrous diet. So that's why we separated the two data.
Yes, but my question, that comes still.
Yeah.